Good morning, good afternoon, and good evening, ladies and gentlemen. Welcome to today's Envy Asia webinar on mitigating incremental short circuit fault levels in electrical systems, sponsored by GNW Electric. My name is Emily, and I will be your host for this session. Thank you for being here. Before we begin, please allow me to go through with you a few housekeeping notes. As you notice, this webinar is being recorded, and the recording will be shared with all registrants afterwards. All participants are muted to ensure audio clarity. If you have any questions during the presentation, please type them into the Q&A box located at the bottom of your screen. We will address as many questions as possible during the Q&A session. We are also happy to welcome two distinguished experts from GNW Electric with us today. Andrew Garcia, Power System Analyst, and Jimmy Bao, Global Product Manager for CLIP at GNW Electric. Without further ado, please allow me to pass the time over to the speakers. Andrew, Jimmy, the stage is yours.
Nice to meet you, everybody. My name is Andrew Garcia. I am the Power System Analyst here at GNW, specializing in our current limiting products.
And my name is Jimmy Bo. I am the Global Product Manager for CLIP, Current Limiting Protectors Portfolio within GNW Electric. GNW Electric provides electrical solutions to strengthen the grid. We're a global manufacturer of commercial electrical equipment to make the power grid more resilient and reliable. Today, the purpose of the webinar is to provide you with a better understanding of some devices, traditional and modern, that reduce faults and increase reliability of the critical infrastructure. Next slide, please. At this point, I want to, Emily, to show poll number 1, please. This poll will give us a better taste of our audience. Basically, what we want to, if you play in any of these markets, this webinar will be useful for you. So now I want you to focus on the picture on the right. This is a catastrophic event at a manufacturing facility due to short circuit faults. Why the short circuit faults? What's the reason behind it? Faults are insulation breakdown due to a variety of reasons. That's equipment failure, human error, pollution, or electricity overload. So now I pose the questions to you to the left of that slide. Are you prepared for such events? Is your system rated to prevent these? How can I prevent this from happening? I expect that by the end of this presentation, you guys will have the tools to answer favorably all 3 questions. Next slide, please. Okay, so the grid is changing. That is, it's everywhere, right? It's common knowledge. Technology advancements are driving the need for power grid transformation. And with the ever-increasing demand of reliable energy, electrical systems have been forced to grow to accommodate such demand, which in proportion increases fault levels. This leads to many problems. Increased cost, think repairs of equipment, project delays, think downtime due to such repairs, and safety issues, all the way to cost, loss of life, which you cannot tie a cost to it. Traditional protection may not be sufficient to solve these problems, and that's why we got to look into new current limiting devices as solutions for this problem. Next slide. So why are fault levels increasing? Well, because of this energy demand that is driven by the power revolution. That's what we are at today. And this power revolution is being led by data centers, which include AI. There's a lot of money, a lot of investments being put into AI. Not only that, we also see cloud computing, data mining. Just we also have transportation, the dual flow of energy due to renewables like wind, solar, battery energy storage systems. All of these are just stressing the grid at levels that we haven't faced before. As power distribution systems expand to meet this growing demand, the fault currents on equipment increase proportionally. Next slide, please. So what have we done? How have we solved these problems traditionally? Fuses come to mind right away, right? And two of those are listed here, our backup fuses and current limiting fuses. They interrupt current both in magnitude and duration. We know them very well. They're widely available. They're inexpensive. They're low maintenance. But there's some drawbacks to them, right? Number one, they need replacement. They have limited availability at higher ratings, meaning for the most part, they only go to 600 amps. And they might not be enough to protecting your application. They also lack flexibility due to you have to conform to their TCC curves, right? The time current characteristics of their melting curves. Next slide, please. The other traditional protection would be reactors, also very common in this industry, in utilities, as the vast majority of the audience here in this webinar. These ones do not interrupt time, they only do magnitude, and they're constantly limiting such magnitude. Two examples of these are current limiting reactors, three-phase protection, and then you got your neutral ground reactors, which, just like the name states, it reduces fault currents at ground faults, right? The pros, again, widely available, and they have higher ratings, but the cons, and they're big, is that they're large in size, and also they have both poor power quality. We're talking about those voltage sags introducing those sags to your system, and also low power efficiency, which means that they're constantly reducing your power in your system due to that impedance introduced by the reactor. Next slide. And this slide shows you a comparison on size on both solutions, right? Current limiting fuse and your current limiting reactor. You can notice there how a reactor can be up to 3 stories high, while the current limiting fuse is more compact in size, can get up to that particular one is 1200 millimeters by 600 millimeters, just for reference. Now I'll pass the ball to Andrew, he will talk to you guys about the modern current limiting devices.
Yeah, fantastic, Jimmy. Thank you. Once again, my name is Andrew Garcia. I'm the Power System Analyst here at G&W Electric. I focus on our current limiting portfolio, so I know a lot about these current limiting devices, and I'm glad to be here to talk about you with some of the modern ones today. So, all about those new developments in current limiting. Once again, just to reiterate what Jimmy said before, the grid is changing in a lot of ways. It's changing in ways that make traditional current limiting insufficient for the needs of the grid today. As a result, there's a high demand for different technology, and new advancements are occurring as a result. And these advancements promise faster fault detection, reduced fault durations, and ultimately, the most important part, the reduced let-through energy. And we anticipate that these new technologies are going to be increasingly common over time. We've selected some of these to go over for this presentation. 3 of the biggest potential technologies that you may see in the future. Those are solid-state breakers, superconductors, and current limiting protectors. So to give you an example of modern protection, we'll start with solid state breakers. It's a type of circuit breaker that uses semiconductors instead of mechanical components. There are no mechanical components anymore, no switches, no clink when you open or close the breaker. The big plus for these solid state breakers is that they ultimately clear faults in microseconds, not milliseconds. So a fraction of an electrical cycle. Ultimately, they limit the magnitude and duration of the fault, and since they clear faults in less than half a cycle, they're therefore current limiting devices. As a matter of fact, they almost entirely eliminate arc flash and fault current as a result through those breakers. Now, that sounds way awesome, right? Really good. And you're right. The pros for that are fast operation. Once again, microseconds, not milliseconds. They have a long lifespan. There aren't any mechanical parts that need to be serviced anymore. You have enhanced control because, once again, it's electronic. You have a lot more control over things that are electronic and how it responds to different events than you would just something mechanical. And ultimately, it's going to eliminate arc flash risks from your system and make it a lot safer for any nearby workers or people that are in the area. However, there's some cons to keep in mind when talking about solid state breakers that may put a damper on all of these pros. One is that they're very expensive. It's a newer technology. And once again, electronics tend to not be cheap. There are limited ratings available, and that's because as you go with bigger and bigger ratings with these solid state breakers, they tend to increase pretty dramatically in size. The cons, there's limited maintenance ability as well. If something breaks in here, it's all electronic. You need to replace the whole thing, and that can get very expensive very quickly. You're also at the mercy of whoever you purchase it from for all of your maintenance needs. Probably not something that you can get any technician to go out and test and maintain on their own. Moving on to the next part, another technology that's massively coming on the scene is our superconductors. And we're talking specifically about superconducting wires. And as you see in the name, these are electrical wires made of superconductive material. Now, just a very interesting thing about this is that how superconducting works is that when they're cooled to a low temperature, basically as close to absolute zero as you can, they have almost zero electrical resistance. So what happens if you increase the temperature? Well, you can rapidly increase the resistance of that wire, therefore adding a lot of impedance to the system, therefore decreasing the amount of available fault current. However, if you think about it, you're going to need a pretty long length of cable in order to have that desired current limiting effect. You need to add a lot of impedance to your system in order to do that, but it's something to keep in mind, especially when you are running long lengths of cable, say in designing a transmission system. So pros, very good, zero resistance or near zero resistance. So no power losses or minimal power losses across that length of cable. High current density, basically there's no electrical resistance, so there's a much lower hazard in passing through a large amount of current through these wires, and highly efficient as a result. You need to install less of these wires in order to have the same effect as it would just a regular set of cables. Now, once again, there are a variety of cons to this, just to make sure it doesn't sound too good to be true for the audience. They're very expensive. Once again, superconducting material is not cheap. It's likely to never be entirely very inexpensive either. You're introducing cryogenics to your system, which is not only new, but it can also introduce a new hazard to your system that your workers will need to be aware of. And just to reiterate, once again, in order to massively increase the impedance and therefore limit current, you're going to require a significant cable length. You can see these a lot, superconductors in HVDC transmission system designs. When you're moving a large amount of energy over a long distance, say from a massive solar plant or wind farm to where there's people. And last but definitely not least, you have current limiting protectors. This is a very interesting device that uses a pyrotechnic charge to divert current to a current limiting fuse during a fault. You can think of it as the only thing that is on your system that you really want to explode. It clears faults in 1/4 to 1/2 of a cycle. And since it clears faults in a half cycle or less, it's a current limiting device. Similar to solid state breakers and current limiting fuses, it limits magnitude and duration of fault. This technology has been established for over 40 years, so it's the most established of these modern protective devices on the market. And it's very low resistance. It's a copper bus bar in a normal operation. That's a copper bus bar lined with those pyrotechnic charges, and becomes a current limiting fuse during fault after that pyrotechnic charge activates and diverts all that current to the current limiting fuse. So there are a lot of pros to these devices. They're very low resistance. Basically, you'd have the same amount of resistance as you would in a chunk of copper bus bar, which is negligible. These can go up to much higher ratings than the solid state breakers can or the current limiting fuses can. So a lot of times it's between this and reactors at higher levels of ratings. They have a long lifespan. It's a very simple but genius electronics and pyrotechnic device. So it can last over 20 years plus. And ultimately, since it's electronically activated, it's only going to trigger in the worst case fault scenario. So you don't have to worry about any kind of nuisance trips, say like with current limiting fuses that lack flexibility and only and follow TCC curves. So once again, as with all modern technology, these are expensive. The pyrotechnics may be something that people are wary to use. They might feel it's unsafe. Introduces a new hazard to your system. I will say though that with these devices, those pyrotechnics are completely contained when the clip or current limiting protector triggers. So there's no additional hazard to your workers. And ultimately, as a result of how this works, because it's only designed to trigger in the worst case fault scenarios, it's going to have very limited low-level fault protection. So if you have a small fault on your system, your regular system will have to handle it, your other devices, and this will not trigger. So I believe that there's another poll question at this part, right?
Correct. Yes. Please submit poll number 2. Before attending this presentation, which one of these newer current limiting technologies have you heard of?
Interesting. So we have a pretty decent familiarity in the crowd with at least half of you have heard of some of these technologies. Good to know. I like working with experts. So keeping moving around, we have a visual representation of these different types of technologies. On the left, you see ABB solid state breaker. That you can very much see how simple the interface is and the lack of mechanical parts that come with the device. They even have a nice power button in the upper right corner. You can also see a superconducting cable. It's a bit more complex than the traditional cables you would expect. And you can see it's a very interesting kind of cable design. In the bottom right, you see the current limiting protector, G&W's current limiting protector or clip. And you can see inside the clip interrupter, the bus bar where the pyrotechnic charges are installed. So how do these stack up together? If you have a project you find that your traditional devices aren't sufficient or come up with severe drawbacks, and you're going to consider some modern devices, how do these exactly stack? In terms of cost, they're all going to be pretty costly, but in terms of least costly to most costly, current limiting protectors are definitely going to be a bit less expensive than solid state breakers and superconductors, just due to it being a more mature technology. The solid state breakers are very interesting as well. Once again, superconductors, you need to lay a long length of very expensive superconducting material in order for that to function. In terms of complexity, once again, current limiting protectors take the cake. They're a very simple install device, very simple principle of operation that's very easy to understand, and with a very simple to understand electronic triggering scheme. Solid state breakers come in second. Once you have trained on those devices, they're pretty easy to understand. And basically all you need to understand is really that when you set it, it's that breaker's going to clear that fault in microseconds. Superconductors are the most complex because it's a new type of cable that needs to be laid a long distance. And you also need to be able to set up those cryogenics in the safe to be able to handle them in the safe manner. So you're going to have to train a lot of your personnel. So now, if you want your best bang for your buck on just current limiting, or I shouldn't say bang for your buck, but the best deal for current limiting, solid state breakers are definitely the best case. Once again, they completely clear that fault in microseconds, which virtually eliminates any fault or any exposure to fault energy. Second place comes in current limiting protectors. They very nice current limiting device, limits faults to a significantly lower level. Last is superconductors, just because if you don't have them run for miles or kilometers, they're not going to be able to limit that much fault current. And that same pattern applies once again for arc flash because it's inherently limited to current limiting capabilities. So solid state breakers come in first, current limiting protectors come in second, superconductors come in last. In terms of available ratings, superconductors, of course, are going to be the best because, infinite current density, you can apply them to basically any kind of rated system. Current limiting protectors come in second, as they can go up to very high ratings up to 38 kV, very high continuous, very high short circuit rating. And in last place comes solid state breakers because there are significant trade-offs in terms of size and efficiency as you increase the size of those breakers. Now, in terms of low-level fault protection, solid-state breakers are the best. Superconductors come in second, obviously, because they'll still be adding that impedance to the system. Current limiting protectors come in last because they're not designed to mitigate low-level faults. In terms of power efficiency, once again, superconductors are the best. You can't beat near zero resistance. Current limiting protectors come in second as they're just a bus bar under normal operation. And solid state breakers come in last because it's electronic, and therefore there's a very slight dip in power efficiency when using those devices. And once again, I believe that there's another poll question right here.
Let's finish this slide and poll.
Understanding. I'm a bit more familiar with our current limiting protectors as they're part of our portfolio, so a bit more detail on these. We call them CLIPs, or current limiting protectors. They're electronically sensed and triggered current limiting device. They're very fast acting. They can clear faults in 1/4 to 1/2 of a cycle, which is unmatched at the rating class that these devices are at. Once again, these go up to very high ratings. They're single shot devices, meaning that every time there's a fault, you have to replace the blue cylinders that you see on the images to the right. We go up to very high continuous current rating. Because it's just a copper bus bar in a normal operation, so we can go up to 5,000 amps continuous with these devices, which is unparalleled in terms of providing a device when you compare this to current limiting fuses and solid state breakers. They are outdoor and indoor rated by default, so you don't need to worry about where to install them. Medium voltage and low voltage goes up to 38 kV. And just to emphasize, the fault energy and the result of the any shrapnel from the pyrotechnics going off gets contained safely in those blue cylinders. Only additional hazard you need to worry about is a loud noise, similar to like a small caliber rifle going off. All right, and now for the poll question.
Please, poll number 3. Which features of current limiting protectors do you consider to be most valuable? I also encourage everyone to post your questions in the chat.
Excellent. I agree with a lot of the findings. Continuous current rating and cycle time to clear fault is definitely some of the most impressive aspects of these devices.
Yeah, flexibility on triggering. Interesting that maintenance and commissioning is one of the top ones.
Yeah, maintenance is very simple on these devices as well, if you were curious about that. But just think of it like a very big fuse. So what are these practical applications of current limiting devices? What does that look like? So some of the benefits of using these devices are as follows. You can use lower rated equipment. So let's say there's 60 kA of that fault current available, but you only have 40 kA equipment available. Using a current limiting device could bring the fault current down to a manageable level, so you can use the lower rated equipment and save quite a bit of money or keep your project on time. You can safely operate over-duty equipment longer. Say you have an older facility that has a lot of over-duty equipment. A current limiting device can provide sufficient protection such that now all of your nearby personnel and equipment are completely safe, at least within the confines of just having proper electrical protection. You can parallel sources in the system without needing a system upgrade. So say you have two separate bus tie or two separate switch gears, large switch gears that you want to connect via bus tie to either increase your system capacity or increase reliability. You can then install a current limiting device in that bus tie between the two now connected gears to make sure that both those gears are now properly rated, since the gear would not be initially designed to be connected like that. Ultimately, these devices are also great at reducing arc flash risks and hazards. We can also, once again, last but not least, you don't have to worry about any power quality issues via voltage drop, and you can save some money via increasing your power efficiency issues from using these devices, any of these devices other than current limiting reactors. And ultimately, one of the better features of this too is if you're looking at a project at an older facility with much higher fault current that was initially designed, you can then retrofit that existing system without needing to upgrade your infrastructure. It's all in the same room on the same paths. We do have a question. Question 1, notice that the fault energy is contained in the blue cylinders with the action to the fault energy after that. That's a great question. And the way that works is that the fault energy will be still arcing in that cylinder, but all that fault energy will then get commutated through the other two blue cylinders that you saw in that image in parallel. And what that means is that all that fault current is going to be commutated, fuses are going to melt and extinguish, and that arc is going to be extinguished in the bigger blue cylinder with that bus bar. So what are the best practices for using current limiting devices? You have them specified at the beginning of project. Worst case, you do not need them and you save money. Best case, you just kept the project on time. And worst case, you need to use the clips and you keep your project on time, or you don't need them and you end up saving money. You do want to pay attention to downstream inrush current. That's very important, as downstream inrush current would be indistinguishable from a fault to a lot of these current limiting devices and could end up triggering them. So you need to keep that in mind when you're determining which kind of current limiting device to use, or even if you can use current limiting devices. Just to emphasize that again, when we're talking about these electrical devices, the inrush current of large electrical devices, such as transformers, capacitor banks, can be large enough to trigger a current limiting device.
Let's go ahead and post poll number 4, please. Will you or your organization implement one or more of these newer current limiting technologies in the future?
Excellent. I like to see the enthusiasm for new technology. Good work, guys. All right, so some more of these best practices. Just make sure you understand the user requirements before doing this, just in case you don't want to end up making a mistake if the user is requiring different material than what you're using. Do you want to use a current limiting fuse but want to avoid downtime? Say the customer doesn't want any downtime. You would want to use a reactor or a current limiting protector instead, because the reactor would just passively keep operating and would have no downtime. The current limiting protector can be programmed electronically to only trigger when you absolutely need it. You want to use a reactor, but you want to avoid any power quality issues that might result. You want to use a solid state breaker, current limiting fuse, or current limiting protector instead. Each of these devices would have low impedance and therefore have minimal effect on power quality in your system. There would be virtually no voltage drop. You have limited space. That's going to narrow your options a little. You want to use a current limiting protector, a current limiting fuse. Not have any downtime, use a current limiting reactor. So how do you coordinate these current limiting devices with other protective devices in your system? You want to ensure that the current limiting device being used only trips when absolutely necessary. Minimizing the probability that the current limiting device will trip when the regular protective devices can handle the fault. So when your system can normally handle the fault, your normal devices, you want your regular system to handle that. Well, the current limiting should be as a backup to your system and should only kick in when you absolutely need it. So therefore, you want that current limiting device to have the most ideal TCC curve possible, either through selecting the best possible devices or setting the device to the best possible settings. For devices that operate passively, just make sure to follow your local regulations. And passively, I'm entirely talking about both the reactor and solid state breaker. Make sure to account for inrush current. Once again, that's very important. You don't want the repeated nuisance strippings because you did not think about inrush current from the very beginning of your project.
Let's go ahead and post poll number 5, please. What is your biggest concern in implementing one of these new technologies?
Meantime, maybe you can answer some of these questions. So, Q2, in what situations should we use a neutral earthing resistor and neutral earthing resist reactor? These are both good technologies to use when you're limiting the fault current or ground fault current to your grounding system or just in your system in general. You would want to use a reactor whenever your system can handle the, whenever you're concerned about adding impedance. You would want to use a resistor over reactor whenever you're concerned about the impact of adding extra impedance to your system. Resistor would be desirable to avoid any power quality issues. As for Q3, let's see.
The question is over transmission level.
Yes. So the two current limiting technologies that you want to check out for transmission level substations would be current limiting reactors and superconductors. Superconductors are widely used in transmission level substations, especially HVDC substations. But traditionally, you'd want to use a reactor in order to limit that fault current. Unfortunately, current limiting devices, broadly speaking, have not caught up to the transmission level voltage yet. And for Q4, any voltage level limitation for clip. It goes up to 38 kV. It can handle any voltage below that.
Mm-hmm. Which goes in line with the previous question number 3, which is the distribution level, right? So transmission is at 72 kV and above, and we're talking we're playing 38 kV.
All right. I'm assuming that the poll was answered already. I didn't get to see the results, but oh, there it is. Yes, I could understand how cost would be one of the biggest concerns. We do anticipate that the cost of these devices will go down as the technology matures. Also, lack of knowledge, technological risk, and long-term maintenance are also I would also consider pretty big issues as well. But technological risk and lack of knowledge will go down over time. As a matter of fact, right now we're tackling the lack of knowledge section of that.
Correct. That's why we're here.
Yeah. And in terms of technological risk, yeah, there's always the risk that when you install devices like this in your system, they may respond in a way that you did not intend. But as time goes on, once again, a lot of these risks will become known and you'll be able to accommodate them in your system. Long-term maintenance, also a concern. I could see that being a concern as well. But, well, maintenance can be a concern with just about anything. So let's get into some of the meat and potatoes, some of the more interesting stuff I know you guys are interested in, some real world examples. So here's an example of current limiting reactors being used at a nuclear power plant. So here they used reactors at this nuclear power plant to limit fault current to permit starting of larger pump motors. However, once again, these using large reactors can cause pretty severe power quality issues via voltage drop. How did they solve this issue? They used the clip current limiting protectors to bypass those reactors to avoid that voltage drop from reactor impedance. They also ended up saving the facility money by mitigating that power loss. So how would that reactor bypass look like? You can see an example in the one line below where the current limiting reactor is in parallel with the clip. The reason why this works is because the clip is a low impedance device by its nature under normal operation, meaning that all of the fault current all of the current and fault current will initially just go through the clip. And once the clip triggers and this becomes open, all that fault current will then just get limited by the current limiting reactor, and you would maintain system uptime as a result. Here's another example where clip current limiting protectors protected 121 wind turbines from the grid. Because of this equipment was underrated and was not easily replaced. Specifically, the equipment that was underrated or overdutied was the equipment installed inside the wind turbines, and you only have a very limited amount of space in there. They would not be able to safely energize or energize at all without using the current limiting protectors. So these devices kept their project on time and kept their facility safe. So here's an example of representation of how exactly this looked like. You have the overduty condition without the clip, you risking the system downstream being overdutied, and therefore a system fault could cause the equipment to explode and harm any nearby personnel or other equipment. They install a clip. That clip gets limited limits that fault current to downstream to a rating that's less than the equipment can handle. And now your system is good to go and it's properly protected. Other example with cogeneration at a major US college campus where clip current limiting protectors were used to isolate the cogeneration system from the utility grid during earthquakes. Without the clip, the system would be underrated and dangerous under these circumstances. There's an example of how this will work for cogen. Under normal operation, the downstream system is underrated, meaning that that equipment could fail and harm any nearby personnel or equipment. With the clip installed at that tiebreaker, now that the clip is going to then split that bus into 1/4 to 1/2 cycle in a fault, and now your normal system can handle the fault. It's not going to fail, and you guys are completely safe. So what is the conclusion? What
Should we answer some of the questions in the
yeah, let's answer some of the questions. Sure.
Yeah. We have question number 5. What will be the most recommended widely used current limiting device for distribution level? So we've talked about
distribution level, generally up to 38 kV. Current limiting protectors go up to 38 kV as a result. They're widely used at distribution level. You could use current limiting fuses at the distribution level. Backup fuses and current limiting fuses are very, very common. Reactors are also a very common device you see in the distribution level. Basically, any of these devices could be used at the distribution level. Superconductors are not common at all yet right now at the distribution level, but as time goes on, I definitely expect to see more and more of that playing it, especially with the power demands from data centers.
So to add to that, I think that the answer to that is depending on, you explain the pros and cons of all of them. So you got to analyze.
At the distribution level and at the low voltage level, you guys have a lot of options. Basically, any of these are possible at that level, and you need to weigh the pros and cons.
Right.
Are current limiting reactors installed in the individual feeders? FYI, this is a 1/2 breaker substation. Usually, there's a attachment to each phase of the system. Whether that looks like there's 3 individuals or not, but it'll just, or 3 individual feeders or not, it's up to the design of that reactor. But generally, reactors are going to look like exactly in that image I showed you guys previously. Are there available current limiters for DC application? Currently, no, but that is something that we are considering for the future. Right now, for DC application, one of the best things to consider would be those superconductors at the high voltage level. All right.
We're done with the question. I think go ahead with the conclusion.
Yep, conclusion. So what are some future trends? Current limiting devices are going to continue to evolve. And these devices are going to focus on limiting the magnitude of the fault and limiting the time that the fault, the duration of the fault. Because that's going to limit the amount of hazard and going to bring down that fault curve to a manageable level. What that means is that new technology may evolve that is not currently in this presentation, and it's important to keep an eye on what's going on in the world. They're going to be used more often as the grid evolves and changes. Once again, the grid is undergoing a revolution, as Jimmy put it. And as this revolution occurs, fault currents are definitely going to increase. And there's going to be a greater and greater need for a lot of these devices, both traditional and modern. And specifically, we do anticipate that superconductors, solid state breakers, and current limiting protectors are going to become a lot more common in the future. So what are the key points and takeaways that I would like you guys to take away from this presentation? The grid is changing. There's energy revolution, data centers, renewables, distributed energy resources, all the typical stuff that the industry has been talking about the last couple of years. It's happening, and it's changing the grid in ways that we both anticipate and probably in ways that we can't anticipate. And as a result of this changing grid, there's going to be a much higher importance on current limitation, because as that grid changes, it's anticipated that the available fault current is going to go up. As you plug in all this new generation via renewables, battery energy storage systems, and new load via data centers. Hope that you came away with a good idea of what traditional current limiting options are available and how to apply them given systems, what the pros and cons are. So specifically with current limiting fuses and with current limiting reactors. And hopefully you guys also got a good overview of modern current limiting devices. Superconductors, solid state breakers, current limiting protectors, what the pros and cons are for these devices, and make sure to keep an eye on these technologies as the grid changes, as they'll become a lot more common. You'll also learn how to implement many of these technologies in your system. Any traditional or modern current limiting devices do come with some caveats on how to implement them, and you do need to keep those in mind. And hopefully the real world examples I gave you some ideas of how you would apply these devices in your systems in order to improve reliability, improve power quality, just generally improve your system.
At this time, can we post poll number 6, please? So do you feel more confident in applying current limiting devices to a system after watching this presentation?
All right, I'm going to go ahead and answer some of these questions. Question 9, is there special competency that could apply for this installation of current limiting devices? It would depend. So for example, the traditional devices, no. Current limiting reactors and current limiting fuses, very standard, very simple devices to both maintain and test. All right, good to hear that this was effective in getting you guys to implement some of these cool new technologies. But to go back to that question, definitely there will be some additional competencies with superconductors, because once again, superconducting involves using cryogenics to bring those cables down to low temperatures. That could introduce an extra hazard in your system, and definitely handling those cryogenic systems is going to require some extra specialization in your workers. Furthermore, in regards to solid state breakers, these are new devices, completely electronic. You guys likely need to be trained by that whatever company that you purchased them from, and to be able to maintain this and test these systems and ensure that you're setting them up correctly. And I would say that the same sentiment applies to current limiting protectors as well. You need to engage the company, in that case G&W, to be able to ensure that, one, they're being used well, and that you understand how they're installed and how they are maintained. So what is the recommendation to limit fault current caused by the concentration of generators at a certain substation greater than 40 kA? There's a variety of different options that you can have. Once again, going back in the presentation, if voltage drop isn't a concern, then I'm assuming that current limiting fuses wouldn't be able to be used here, because that is a larger fault current. So current limiting reactors would be one of the traditional options to use here, especially if voltage drop on your system is not considered an issue. Otherwise, you're going to need to look at the modern protection. Current limiting protectors have been used commonly in this situation where you have a lot of generation or cogeneration in the facility. You need to limit it to from above 40 kA to 40 kA or less. Solid state breakers may also be an option, as well as the continuous current and voltage class is not too high. Yes. What is the effect of voltage surge or lightning strike to a current limiting device in terms of its operation or functionality? That entirely depends. I'm not certain exactly how the lightning strike would affect a solid state breaker, for example. It's an electronic device. I assume that they do have some method that I'm not too familiar with, and how to limit the effect that a lightning strike or voltage surge could cause on that system. However, in a lot of the other devices, current limiting protectors and the traditional devices like reactors and fuses, lightning strike would probably have a minimal effect on your system, provided that the lightning strike or voltage surge does not exceed the level that your system is rated for in terms of impulse voltage.
Right.
In which case you could have a flashover, but that's going to happen current limiting device or any other device in your system. What is the utilities practices that they discovered that the short circuit level higher than the rated design? Based on your experiences, do they replace their equipment or consider the current limiting devices solutions by statistics? Traditionally, utilities have relied on going with higher rated equipment, but that's what we're seeing, though, once again, as the power grid revolution is happening, is that that's no longer entirely a practical solution, because the higher ratings they may need may not be readily available. Lead times may be high. They may need to import them from a different country, or it might just not be possible at the ratings they need. So more and more, the statistics are leaning towards these companies or utilities looking at current limiting devices as a solution. Both
and I'll add to that,
and modern devices.
I'll add to that question, that instance happens more often than you would think nowadays. And yes, they're turning to current limiting devices as a solution over the more costly and time delay solution of replacing all the equipment.
Yep. Next question. Mentioning that the clip will bypass the existing reactor, does it mean that the reactor is not required anymore after installing clip? In terms of current limitation, maybe not, but what this means is that when you do it and bypass it, it means that when the clip does trigger, because the clip is going to open, like ultimately be an open device once it triggers. So that circuit's going to open. That would mean if there was just the clip installed in the system, your system's going to go down. If that's the only source that you're getting electricity from, it's going to segment that. Your system's going down. Having the reactor in parallel means that all that current is then going to get commutated after the clip opens to that reactor. That's going to mitigate any risks of downtime in your system. But once the clip does open and you're running the reactor, you are going to have the power quality issues that you're trying to avoid.
Think of it as the best of both worlds, where you're experiencing during normal operation, no power losses, no voltage sags. But when there is an event and a triggering event of the clip, then you have no downtime, but the reactor kicks in.
Sir, do you have an example of protection coordination with current limiting devices and smart inverters protection and how they respond to each other if there is a fault at the connection? Thank you. If there's a fault at the connection point, that shouldn't affect how the current limiting devices activate or coordinate, so long as there's enough current in the system to cause the current limiting effect from that current limiting device to kick in. For example, with the current limiting protector, that current exceeds the whatever the device is programmed to trigger it, then the clip is going to react to that fault and clear that fault, regardless of how the smart inverter responds to that. Reactors are going to operate passively, meaning that regardless of the behavior of the inverter, the current limiting reactor is always going to passively reduce fault current. They're always going to have that extra impedance to your system. As for solid state breakers, I'm assuming that the way that they're designed, you wouldn't have any issues with how downstream electronics operate in comparison to the solid state breakers. Superconductors are also pretty simple. Fault current exceeds a certain level, it's going to send a signal, get rid of those cryogenics, temperature is going to increase rapidly, impedance goes up, current goes down, regardless of how the inverter operates. Question 15, continuation, maybe a separate discussion. Yeah, if you guys want a separate discussion on this, on any
I think you missed the first one. Can we have a further discussion if current limiting devices can be applicable to our problems? And yeah, separate discussion.
Yeah, we can have a further discussion. I don't know if we'll have enough time to do it right here in this presentation, but if we get your input, you're more than willing to,
I'll say absolutely. I don't know, Emily,
absolutely.
who can chime in. If you can chime in on the providing our contact information, but yes, we're more than readily available. I'll also ask that the 18% that really didn't get some of the voted, that didn't get all the technology or the advancements of the current limiting devices, please reach out for another explanation if you need to.
Okay.
Great.
All right, hand it back to the Unlit Asia folks.
Thank you so much. I think that is a good point to wrap up the discussion for today. Thank you so much to our speakers, Andrew and Jimmy, for your expertise, and all of you for your active participation. We will upload this video after this session, and for more information on upcoming events, feel free to check out on the Asia website. Thank you once again, and have a great day ahead.